So next we want to find the center of mass here of a plate of uniform density. So our plate is going to be the region that is under this graph of y equal f of x. And between A, which looks like it's about 0.5, and B, which equals 5. So remember when we found areas underneath the graph of a function, we would approximate it with areas of rectangles and sum up the areas of the rectangles, and then take a limit as you took more and more rectangles and their width here got smaller and smaller. Well, we can do something similar with the center of mass using additivity of moments. So we approximate the area with a bunch of rectangles. So we partition our interval AB up, and those are the bases of the rectangles. And then let's take one of these rectangles out, for example, this one. And we want to find the centroid of just that rectangle, that approximated rectangle. Well, that's not hard to do. This is uniform density, so the balance point should be here in the center. Well, that's reinforced by what's called the symmetry principle, which says if you have a region R and it's symmetric about a line L, then the centroid of that region has to be on the line L. Well, this rectangle is symmetric about the lines that cut the area in half. So these midpoints, or midlines. So by symmetry, we get our centroid there of the rectangle. So, and then also remember that mass is density times area if you're talking about a lamina. Remember, rho is density. And then what is the area of that rectangle? Well, we've got x and y, we've got x coordinates, down here. I'll call them xi minus 1 and xi. And then the coordinate at the midpoint there is going to be, we'll call that xi bar for the midpoint of the base. So if we go up to the height here, that height is going to be the function value, right? Because we're using sort of a midpoint here. So the height we can approximate with the function value at xi bar. And then the base is just going to be delta x. So here's our height times our base, which is equal to area, height, base. And then that means that the moment about the y-axis for that rectangle r sub I is going to be the mass times the x-coordinate of the centroid of that region, xi bar. And what is our mass here again? Well, that's density rho times area f of xi bar delta x. So this is our rho times area is mass. So we get rho times f of xi bar delta x times xi bar. So then you add the moments, add the y moments over all these rectangles. That's a property of moments, that if you have these regions that are next to each other, that you can add the moments. It's called additivity of moments. And then you take a limit as n goes to infinity, so more and more approximating rectangles. So then the base of those rectangles, delta x, is going to approach 0. And when you do that, your y moment then is going to be the limit as n goes to infinity, and that means error in the approximation goes to 0, of the sum of rho xi bar f of xi bar delta x. That's this right here. So it's the sum of these guys, sum of mass times x coordinate, which is what y moment is. And when you take a limit of a sum, you get an integral. And the constant rho we factored out in front, right here it is. Xi bar turns into x in the limit, f of xi bar, f of x, and delta x dx. And then you can do something similar here with the x moment here. The x moment of that region is going to be rho times f of xi bar times delta x. So that's our mass here times density or I'm sorry, area times density, which is mass. So this is mass. That's m sub I. And then here, this is y bar. That's the y coordinate of the centroid here. This is f of xi bar, and this distance is 1/2 f of xi bar. So since that's the balance point, it's just like saying that all the mass of the rectangle is at that balance point. So this is mass times the y coordinate. So we're summing up mass times y coordinate. So then your total moment, m sub x, is going to be the sum of, this is mass here, times y coordinate. And then we're going to take a limit again as n goes to infinity. So the rho can factor out, the sum turns into an integral, and then f of xi bar turns into f of x, and we got another f of xi bar, so there's two f of x's, and then the 1/2 right here. So we left the 1/2 inside. So those are our x and y moments. So then that means that our center of mass, x bar, is going to be the y moment divided by total mass. So here's our y moment formula, which is right here. And then the mass is density times area, and then notice that density cancels. So we're dividing by area. I'm just going to write that as 1 over area out in front times the integral of x f of x. So here's the summary of that first formula. And then the y coordinate of the centroid is going to be the x moment divided by total mass. So here's our x moment right here. And then here's our total mass. Density cancels again. So we've got now 1 over area here, and then the integral of 1/2 f of x squared. So that's this formula. So here's the summary of those two formulas, but I just wanted to show you how those derive. So that's for a region that's underneath the graph of a function. Now, if your region is between two functions, so we've got an upper function here, f of x, and lower function, g of x. And what we want is we want the balance point of this region here that's in between the two functions. So we want balance point of that region right there. So what do? Well, 1 over the area, and remember area you get by doing integral of f minus g, and then instead of integrating x f of x, you integrate x times f of x minus g of x. Okay, so that's the vertical distance between those functions. And for the y coordinate of the centroid, 1 over area, and then we do 1/2 f of x squared minus g of x squared. So you subtract the functions or subtract the squares, just like when you're finding area between the functions, you subtract the two functions. So notice that pattern. And the reason that this all works just comes from the geometry of approximating here with rectangles. The base is still going to be delta x, but the height of those rectangles is going to be f of x minus g of x. And then it's looking at the x and y coordinates of the centroid of that approximating rectangle. So that's where the subtractions come from in here. And it's a similar analysis to what we did up here, except the height is not f of x, the height is f of x minus g of x, top minus bottom. So that changes coordinates of this centroid, but it's still what we're doing down here, mass times y coordinate, and here, let's see, where we go, mass, sorry, that's here, mass times x coordinate. So mass y coordinate and mass x coordinate, just as we did in the analysis here.